Hi everyone, welcome to the next half of this chapter. Last time we have covered quite a bit of factors related to pavement design. Let me go back and to do a little recap here. We talked about that flexible pavement design can be done using the ASHTO 1993 or the ASHTO Institute method. We said we're going to cover 1993 ASHTO design method. We've talked about different factors that gets into the design from what is the definition of the performance period versus the analysis period, and then the payment performance in terms of the serviceability index. So we can start from an initial serviceability index, roughly about 4.2 for flexible pavement, and with time we need to determine what's failure criteria for any one of the functional classification of highways. So if it's an interstate, we determine that the terminal serviceability equal to 3. If it's all the way down to collector or local street, we consider it equal to 2.0. And then we define what's the serviceability loss, which is delta PSI, the difference between the initial serviceability and the terminal serviceability. Then we talked about traffic and the cumulative ESLs, equivalent single axle loads, and how can we do the corrections. And then also we talked about material consideration when it comes to the soil, the strength of the soil, the residual modulus, the drainage coefficients, the layer coefficients. So we've covered quite a bit of that, including again the K value and how did we come up with the effective residual modulus. Not the K value, I'll take that back. It's the effective residual modulus, MR. The K value is going to be for the Portland semi-concrete, not for flexible pavement. And we did again we got the layer coefficient for the flexible pavement using this graph right here, and we did get the A2 and A3, which is the layer coefficient for the second and third layer from the equations that I showed you here. We finished last time with the drainage coefficients. We got to know that drainage coefficients get assigned to the second and third layer. That's why we have an M2 and M3, and we got to pick those from this example right here. Let me remind you again. So we had here a pavement design with a fair drainage, which is, again, that means it's a 1 week. Therefore, I would know that this is the line that I'm going to pick from. And then the other criteria for drainage is I have 2 months per year. That means about 16% of the time or of the year I'm having a full saturation condition. Therefore, it's in this column right here. So that's why the M2 and M3 will be ranging from 0.8 to 1. One of the last factors that we need to consider in our pavement design is the reliability level. As I briefly talked about it last time, reliability level, it actually relates to how confident are you with your design. If you are designing a pavement with a 99.9% reliability level, that means this pavement has a very high reliability. Therefore, this section has a percentage chance, a high percentage chance, let's say 99.9%, that this is gonna last for the analysis period. For example, if you design the pavement for 40 years, it's gonna last for 40 years. If you design it for 20 years, it's gonna last for 20 years. But if you design it with a 50% reliability, that therefore this means there's a 50% chance that this design will last for 20 years. But there's also another 50% chance that it will not last for 20 years and it will have a premature failure. So that's why we need to talk about reliability and what's the level of reliability that we need to pick. For flexible payments, there are two methods for when it comes to reliability determination. The first one is a deterministic approach, which means that each design factor has a fixed value, which is based on the factor of safety assigned by the designer. And this can result to an over-design or an under-design approach because sometimes we're going to end up assigning higher factor of safety for those factors that are less certain or that have a greater effect on the final design. So that means, again, we have a blind view here of what's going on and all the factors that gets into the pavement design, and we're going to assign a fixed value no matter what. And that's why, again, I can have, if this determination or this fixed value is very high, that means I'm going to have an over design, which is going to cost me too much to construct this road, or I may have an under design. The better way of doing it is actually the probabilistic analysis or approach, where it's more realistic. And the reason why it is that way, because each design factor is assigned an average or a mean and a standard deviation. So the reliability here is defined as the probability that the design will perform its intended function over its design life. So to deal with reliability and pavement design approach, we define two factors here that we need to determine or we need to obtain. The first one is the overall standard deviation, which is S node. It's this factor actually basically it takes into account the error due to the variability and estimating traffic or the material strength and construction practices, and it ranges really from zero point 0.3 to zero point 0.5. A typical number for standard deviation for flexible pavement is about 0.45 for flexible pavement. ZR, another factor, this is probability, the probability that the serviceability will be maintained over the design life of the pavement, or in other words, simpler terms, is probability that the pavement will perform at or above the terminal serviceability during the design period, PT, if you recall. So these two factors together, this S node and the ZR, will be used together to ensure the likelihood that the pavement performs at the expected level or even higher. R, the reliability level will be taken from the table that I'm going to show in a little bit, which is 11.14. And for stage construction, sometimes if you are intending to build a highway at different stages, so the reliability for the stage for certain stages is equal to the reliability of the overall project, or to the power of 1 over n, and n is number of years. So this is the table that we will be using a lot in our pavement design examples. So let's take a look at this here. So if I have, this is the functional classification, and here we have the recommended level of reliability depending on if it's an urban, if this structure is residing on an urban or a rural setting. So for example, if I have an interstate or any other type of freeway, and it's an urban environment, so the reliability level will be somewhere between 85 and 99.9%, which is considered the highest reliability level within this table. If it's in a rural setting, we can lower the reliability level a little bit to reach from 80 to 99.9. And the list goes on down all the way to a local street. If I'm building a local street, then I can reduce my reliability level to reach somewhere between 50 and 80, regardless if it's urban or a rural setting. So you can tell here it all depends on the importance and the classification of this roadway. So for example, if I am having an interstate system, I cannot afford having a low reliability highway or freeway, meaning that I can't afford closing this highway if I have premature failure every few years. I can't close it due to traffic. I can't even close one lane at a time, because again, there's gonna be a lot of traffic issues, traffic jams, and maybe even increased number of accidents. While for local streets, I can lower that reliability level a little bit if desired. So based on all the equations and based on all the parameters that we've talked about, we come up with this design equation that all design factors are linked together in one single equation. So let's take a look at this equation, and then I'm going to show you the nomograph, which is this is the more frequent approach that the engineers use instead of the equation. But this equation, I have seen students before they will program it on an Excel file to get them what we are after, which is this factor right here. This is the structural number. So let's take a look at this here. The log of W18. W18, I hope you know it by now, this is the equivalent single axle loads for the design of the pavement. ZR and S node, this is the reliability level calculations, and then plus 9.36 log of the structure number plus 1 minus zero point 0.2 plus log of delta psi over 2.7. What's delta psi? This is the pi, the initial serviceability, over the PT, which is the terminal serviceability, over zero point 0.4 plus 1, 0.094 over Sn plus 1 to the power 5.19. And again, this is the unknown that we need that we need to obtain, plus 2.32 log of the Resident modulus minus 8.07. As you could tell, that this equation has weird factors here, that there's no, again, reason why they are exactly this way. That's why this equation is very empirical, and it will be provided to you in an exam in case you need it. So this equation, again, we use it to estimate the structural number, or we can, the actual pavement engineers at that time, they solved this equation in a term of a nomograph that typically now most of pavement engineers use it instead of implementing the equation. The MR in this equation, again, this is for the subgrade if the structural number considered for the entire pavement structure, but we're going to see in more details that MR can be E1 or E2 or E3 in some cases. But again, I'll leave this to the example later on. So here are the explanation of each one of the factors that are mentioned in this equation for your reference. And this is the famous nomograph that we will use as pavement engineers across the board. It's used by many state DOTs across the United States, and it's the state of the art still and overseas. So what do we see in this example? And I'm going to explain to you first afterwards what's the importance of the output of this nomograph, which is the structural number. Let's take a look at here. The graph, or the nomograph rather, starts from the left side with the reliability level. What should be our reliability level? So we will pick this based on the road classification that we're designing. Then we're going to connect the reliability level, let's say at this point here, which is 95%. This is an example. We're going to connect the point here from 95% to the overall standard deviation. The overall standard deviation is, in this case, so in this example, is 0.35. So this is here 0.2, this is here, the exact tick mark here is 0.2, this is 0.4, this is 0.6, and that's why, therefore, this is, if this is 0.2, this line here is 0.25, and this is 0.3, and this is 0.35. So we connect this point to this point here by a line like this, and then until you hit this line. We call this TL. This is a turning line. Again, it's nothing scientific here. It's a connection point from this line to what's next. That's really what the TL is all about. And there will be another one coming up here as well. So we connect this point from the turning line to the next input, which is the estimated total 18 kip equivalent single axle load. This is the W18. This is the estimated easels for the design life of the pavement. So here in this case, we're expecting to have 5 million easels for the next, again, years to come. So this is also a log scale. I have here 0.5 millions, because by the way, this is in millions, as you can see here. So I have 5 million. So this is 1 million, this is 5 million, this is 10, and this is 50. This is all logarithmic scale. So I'm going to connect the point from here to the 5 million until it hit the other turning line. So now I'm going to approach this point right here. So from here, I need to connect it to the next point, which is, this is the effective resilient modulus. What's the modulus, or what's the E value? The E value in this case is 5,000 psi. So again, this is log scale from 1 to 5, and this is in KSI, by the way. KSI meaning that if it's 5,000 psi, that this is equal to 5 KSI. K stands for 1,000. So instead of 5,000 pounds per square inch, you can say again 5 KSI. So this is 1, this is 5, this is 5,000, this is 10, 20, and 40,000. So I'm going to connect it to the 5,000 point right here, and that's why we connect the line from the turning line to here, and we'll extend this line until we hit the y-axis of this graph right here. This graph right here again, and once we hit this point on this y-axis, you're gonna draw a horizontal line across the board until you hit one of these lines. What are these lines represent? These lines represent the delta psi, which is pi, the initial serviceability, minus the terminal serviceability. So I was told in this example that the delta psi is 1.9. So this line is 0.5, this is 1, this is 1, this is 1.5. So, and this is 2, so between 1.5 and 2, which is close to 2, I'm gonna draw the line, draw a vertical line until I hit what I'm looking at here, this one right here, the structural number. So the solution, the structural number is equal to 5. We're going to go through this nomograph multiple times, but I hope again you can rewind the video here to understand how did we go from reliability level to standard deviation to the turning point to the ESLs, another turning line to the modulus or the modulus value until we hit the y-axis. We go to pick one of these delta PSI lines, go down to get the structural number, and that's what we are after. Why we're after a structural number is because we're gonna follow this equation. So these are actually the why I explain for you why we're after the structural number. So the required structural number, actually the structural number by definition, again, it gives us an indication what's the strength of the pavement. What's the strength? The strength of the pavement um, represented by the structural number, which is a function of the layer thickness, the layer coefficient, the drainage coefficient. So the structural number is equal to AI, which is the layer coefficient, which we talked about last time, times the thickness, times the drainage coefficient. So if we get the structural number from the nomograph, and I know what's the layer coefficient based on what we discussed last lecture, I also get to know how to get the drainage coefficient. So what's left? What's left actually is what I'm looking for, which is the thickness of each layer. And that's what pavement design is all about. Again, if I'm designing a 3-layer system, let's say again I have an HMA layer, I have a base, I have a sub-base, and all this on top of the soil or the subgrade. My goal after this procedure is to get the thickness of each one of these layers, which is D1, D2, and D3. All right, so how we do this? What's the procedure then? The procedure is as follows. So we need to select a set of thicknesses. So that provides the following. So the overall structural number for the whole structure, the needed structural number, is equal to A1 times D1, which is the layer coefficient for the top layer times the thickness of the first layer plus A2 times D2 times M2 plus A3 times D3 times M3. This has to be more than the required structural number that we get, more or equal to the required structural number we got from the nomograph. So A1, A2, A3, these are the layer coefficients for the surface layer, the hot mix asphalt layer, the base and sub-base, and D1, D2, D3, these are the thicknesses for each one of these layers. So how can we go after this is by looking at this procedure here and this schematic. So we have 3-layer system that we need to solve for, that they are on top of the road bed course or the road bed soil. So we have the first layer, second layer, and third layer. The way we do this is we're gonna do it one step at a time. So for the first layer, it has a modulus E1 and a layer coefficient A1. Second layer is going to have a modulus layer E2, and it's going to have a layer coefficient E2, and it's going to have a drainage coefficient M2. The third layer is going to have an E3 modulus E3 and the layer coefficient A3 and the drainage coefficient M3, and the bottom layer is going to be the resilient modulus or E, but we like to call it MR for the soil sample. So the way we do it, the procedure thickness design starts from the top to the bottom. So what we're going to do, we need first to design the top layer, the surface course layer. We need to get D1. The way we do this is, as I told you, we're going to go through this nomograph 3 times if I'm designing 3 layers. So, but the first thing, the philosophy behind the pavement design is I need now to determine what's the required thickness of the base course which is going to correspond to the structure number one, that's going to protect the layers underneath that layer. Once I'm done with the first layer, I'm going to go now to the base layer, and now I'll be interested to know what's the required thickness of both base course and the surface course and the base course to protect the sub base and the sub base course and the road bed course. And then I'm going to design for the third time the sub base course thickness as well as the base and the HMA layer to support and protect the subgrade. What does that mean? Let's go through the procedure so everyone will understand. So the very first step is we are going to now get the structural number one because we need to design the top layer. And as I said, since we're designing one layer at a time, to get to the first for the first time we get to the nomograph, I'm gonna need to design this layer, and to design this layer I need to when I get to the structural to the nomograph like what we had here, everything is gonna be known to me, but I need to make you aware of one thing that's a tricky point here. If you're designing the top layer, once you get to this stage here, the E, you need to use the layer underneath it because now you're designing. Let's say I'm going to design a hot mix asphalt layer. The hot mix asphalt layer will have to protect what's underneath it. That's why I'm going to put the E2 of what's the road bed, or this is the effective road bed soil resilient modulus. Remember, this is not supposed to be the modulus of the current layer I'm designing. This is supposed to be the modulus of the layer underneath the layer that I'm designing, and that's the key point. So, for example, that's why here you see to get the thickness of the top layer, what I'm going to do, I'm going to use E2 as the MR to determine the structure number one. Once you get the structure number one from the nomograph, I'm going to say the structure number one is equal to D1 times A1. I know A1, I know structure number one. So if I divide structure number one over A1, I should be able to get D1, or sometimes we call it D1 prime. Why we call D1 prime? Because again, D1 prime will be rounded up to the nearest half an inch. Let's say you got structure number one. Well, let's put numbers here. I'm gonna use my calculator as a backup. So let's say the structure number one. I'm gonna just assume a number. Let's say structure number one equal to 3.2, and A1 is equal to, let's go back to A1 values from the previous lecture to pick a correct number. Let's say A1 is 0.44. So I'm going to come back to here and say A1 is equal to 0.44. Therefore, D1 now will be equal to 3.2 over 0.44, and that would give me a layer thickness equal to let's say 3.2 over 0.44. That means 7.27. So the exact thickness that I really need is 7.27 inches. You can't give a contractor a thickness that's 7.27 inches. Typically what we do, we round it up to the nearest half an inch, like what we see here. And then, so which means instead of 7.27, I need 7.5 inches. So what happened now, I need to revise the structural number one. The structure number one is not SN1 anymore, it's SN1 prime or SN1 star. Why is this? Because now I don't have 7.27, I have a thicker structure. So what we do, we say, okay, instead of 7.27, it's gonna be now 7.5. And this is the thickness. Therefore, the new structure number one, SN1 prime, is equal to 7.5 times A1, which is the same, 0.44, which is going to be equal to, so it's 7.5 times 0.44. This is equal to 3.3 instead of 3.2. So 3.3. So this is how you get the first layer. The second step, now the same thing is going to be now for the second layer. I'm interested now to get the thickness of the base layer. So if I really want to draw this again, I have the top layer, the base, and the sub base. I got the top layer already, which is 7.5 inches. Let's say now I need to go one more time through the nomograph. I'm going to use now E3 as the MR value. Why? Because if I'm designing the second layer, and now I'm gonna use the layer underneath it as the support layer. So that's why I'm gonna get to the nomograph using E3 and to get SN2. Once I get SN2, this SN2 is actually, these numbers are cumulative. So SN2 will be representing SN1 that you got from the first layer. And instead of following this, you can follow the equation that I'm showing you. SN1 plus D2 times M2 times A2. So SN2, you'll get this from the nomograph. SN1 is known to you now. Again, it's 3.3. So this is here is going to be 3.3. And SN2, let's say SN2 is 4. You got it from the nomograph. And now D2, this is the unknown to me, times M2. Let's say M2 similar to the problem that we did last time. Let's say it's 0.8. And A2, let's say is 0.15. So the unknown here is D2. So to get D2 here, you can do your calculation. You need to subtract 4 minus 3.3, so it's 0.7, then over 0.8 over 0.15, and therefore the thickness of the second layer is 5.83. Please do the calculation. You're going to arrive that D2 is equal to 5.83 inches. Again, same thing, similar to what we did for step 1. I need to round D2 to the nearest half an inch. So that 5.83 is going to be rounded to 6 inches. Once I have now 6 inches, I need to revise SN2. So again, remember, pyramid design is cumulative. So SN2 revised, or SN2 star, is actually now the 3.3, which came from the top layer, plus not 5.83 inches anymore, it's 6 inches, times M2, which doesn't change, 0.8, times A2, which is 0.15. Again, please forgive my handwriting here. I'm using my mouse actually. So the new SN2 now is not 4 anymore. It's actually 6 times 0.8 times 0.15 plus 3.3. So it's 4.02. Again, there's a difference between 4 and 4.02, trust me. So keep it 4.02. So now we got the second layer thickness, which is equal to 6 inches. All right. So now we're down to the third layer. The third layer, I need to revise. This is actually the third step, not the second. So the third layer is the same exact thing. I have now SN3. How are we gonna get to the nomograph? Since I'm designing the third layer, which is which is the sub base, and now I need to use the modulus underneath it to get to the nomograph, which is in this case the resilient modulus of the soil. So once I get this from the nomograph, SN3 now will be SN2 star, which is coming from the first two layers, plus D3 times M3 times A3. So let's say I got SN3 equal to 5, or actually, let's say 5, that's okay. It's just an arbitrary example. SN2 equal to 4.02 from the previous step. This is, again, because it's cumulative, this is coming from the top two layers, plus D3. D3 here, this is the unknown. I don't know the thickness of the third layer yet, times M3, let's say again it's 0.8 times A3, let's say it's 0.1. Therefore, I can get now D3 based on this equation because it's just one single unknown. So what I need to do, I need now to subtract 5 minus 4.2. That's 4.02. 5 minus 4.02. And then I'm going to divide this by zero point 0.8 and by zero point 0.1. So the required amount of thickness for the third layer is 12.25 inches. 12.25 inches. And again, I'm going to round this third layer to the nearest half an inch. Therefore, it will be 12.5 inches. And then lastly now, I will need to update the overall SN3. So SN3 star will be equal to the SN2 star, which is already known 4.02, and then plus D3 now star, which is 12 and a half times zero point 0.8 times zero point 0.1, and that hopefully it will be more than 5. So I have 12 and a half inches times zero point 0.8 times zero point 0.1 plus 4.02, that is 5.02, which is higher than what's needed, which is 5, and therefore now the design is complete. I can go back to here. I need now the third layer to be 12 and a half inches. And with this, I finish my design. This is just again to satisfy that yes, this is what we did. SN1, SN2 is 3, it's a cumulative. That's what we did. That's what we did here to arrive that the design is satisfactory. I hope again you understood the procedure, and in case you couldn't follow exactly all the steps, again you can rewind and listen to it one more time. But also I have a great example here for you that can be of a great help to reinforce the concept. So let's go through the example together. So using the ASHTO flexible pavement design procedure, design a pavement for a 6-lane both directions, which means 3 lanes per direction, and it's a rural interstate highway. And if you wonder why I'm putting this in bold, because this is gonna trigger for me the reliability level needed. Then the expected 30-year design ESL is 15 million per direction. Very important piece of information. And then the pavement structure will be consisting of an asphalt concrete layer with an elastic modulus of 400,000 psi. I'm gonna use this one to get the value of A1 if you recall. Why is this? Again, if you go all the way back to here, this is the graph that I'm talking about. This is where you're gonna get the A1 from. All right, so just if you're wondering. Next, I have a granular base layer. The second layer will be a granular base layer with an elastic modulus of 26,000 psi. Then I have a granular sub-base layer with an elastic modulus of 12,000 psi. And then I have on top, at the bottom of this whole structure, I have a subgrade soil that has a resilient modulus equal to 8,000 psi. And the very last information needed is it's estimated that it will take a week for the water to drain from the pavement surface and that the pavement will be saturated about 15% of the time. Why this information is important? Because this is what's going to trigger for us what's the drainage coefficient value, M2 and M3. So having it for a week, and I have full saturation for 15% of the year. So let's start. How can we go after this? We need to get all the information needed to get into the nomograph. Remember, the bottom line is to get into this graph right here. So you need to obtain the reliability level for this structure. You need to get the standard deviation, the easels, the modulus, and then the delta psi. Once you get to have these 5 parameters, then you'll be able to get to this nomograph. And guess what? How many times you're going to get to this nomograph? You have 3 layers, therefore you're going to get to this nomograph 3 times. And the only thing that's going to change in these 3 runs is this column right here. Again, if you're designing, when you design the first layer, you're going to use E2. When you design the second layer, you're going to use E3. When you're gonna design the third layer, you're gonna use the E of or the Residual modulus of the soil. That's pretty much what it is. So let's start with the one of the simple things that get us to this number graph is the reliability level. So it was told to us as a rural interstate highway. So for a rural interstate, so it's interstate, so I know the classification. It's not a principal arterial, it's not a collector, it's not a local, it's an interstate, and it's in a rural setting. That means the reliability level will be somewhere between 80 to 99.9%. I picked here reliability level of 90 as a midpoint. Again, if you pick 80, that's fine. If you pick 99.9, that's okay, but I picked somewhere in between. Next, I need to get what's the serviceability index or delta PSI. Remember, we had the PI minus PT, and this is going to be equal to the delta PSI. Okay, so the PI, the initial serviceability, if it's given to you specifically for this problem, you can use it, but if not, typically for any new flexible pavement roadway, it's 4.2 minus PT. The thermal serviceability is depending on the importance of this highway. So if you go back to all the way back to the table that we discussed last time, when it comes to the thermal serviceability, it's this table right here. So if it's an interstate, the thermal serviceability has to be equal to 3. So going back now to our problem, and so therefore this is equal to 3, and therefore delta psi, as I'm mentioning here actually, is 1.2. Next is the S node, which is the standard deviation. Again, this is one of the default values unless if it's given to you, and the typical value for flexible pavement is 0.45. Next is the easels. It was given to you that the easels is 15 million easels per direction, not per lane. Remember, when we did the easel calculation, you need to multiply it by directional factor and the lane distribution factor, unless if it's given to you by the lane or by the direction. So for example, here, it was given to us as 15 million easels per direction. Therefore, there is no directional factor that need to be applied. All what we need to care for now is to multiply this 15 millions by a lane distribution factor, depending on how many lanes per direction. It was given to us as 3 lanes per direction. Therefore, the lane distribution factor will be ranging from 60 to 80%. So I picked somewhere in between, and the lane distribution factor is 70%. Therefore, out of this 15 million easels that I'm expecting, in this one direction, I'm gonna experience 10.5 million easels in the design lane, in the most critical lane, which is 10.5 million easels. Next, I need now to get the layer coefficients. If you recall again, in any SN equation, SN structure number is equal to thickness times structural number. So the structural number for the top layer, remember again, it depends on the modulus of the hot mix asphalt layer. If it's here, it was given to us, it's 400,000 psi. So you're gonna draw a vertical line from 400,000 and then a horizontal line until you get the layer coefficient, which is in this case equal to 0.42. This is for A1. For A2, we're going to use the equation that I showed you last time. So for untreated base, having E2 equal to 26,000, so you can use again either this figure 7.15a, or this equation. A2 is equal to 0.249 times the log of E2 minus 0.977. So this is the equation that you're going to be using here. So we have 0.294 294 times log of 26,000 minus 0.977. So the layer coefficient A2 will be equal to 0.12. Same thing for A3. It's 12,000 psi. You can use the figure 750, 716, or the equation. And again, using this equation, you will be able to obtain the A3 is equal to 0.09. So you got now A1, A2, and A3. Last thing we want to get going here is the drainage coefficient. Remember, it was told to us from the equation I am gonna have 1 week of the water is gonna stay on the surface until drainage happen, and the pavement will be saturated for 15%. If you go back to the table that we talked about last time, if it's for 1 week, it's a fair condition, and I have it for again it was 15%, so it's going to be again between 5 and 25. So the range will be anywhere between zero point 0.8 and 1. You can pick zero point 0.8, you can pick 1, you can pick 0.9. Again, anywhere from that range is acceptable, and I picked again a medium value of zero point 0.9, M2 equal to M3 equal to zero point 0.9. By this now I'm ready actually to design the very first layer. So the very first layer, as you remember, section number 1, I need to design the top layer. So to design the top layer, I need to know, I'm going to use the E of the E2, which is the layer underneath it, the layer that's supporting it. So that's why here I have now I'm putting all the numbers that I got so far, reliability level equal to 90%, structural, the standard deviation equal to 0.45. The ESLs are 10.5 million ESL. Delta PSI is 1.2, and the modulus of the layer, the second layer, is 26,000 PSI. So you're gonna connect again 90% reliability level to the standard deviation, which is 0.45, until you hit the turning line, and then from the turning line you're gonna connect it to 10.5 million ESLs until you hit the second turning line. From the second turning line, you're going to hit the modulus E2 because you're designing the first layer. So E2 is 26,000 psi. You're going to hit the y-axis again at this point, and then you're going to draw a horizontal line. And then from the horizontal line, you're going to pick one of these lines to correspond to delta psi equal to 1.2. So it's between 1 and 1.5. That's why I stopped right here. Therefore, I got the structure number 1 equal to 3.3. So once I get 3.3, again, 3.3 as I showed you, we have now the D1 is equal to SN1 over A1. So 3.3 over the layer coefficient is 0.42. I'm gonna get now the required thickness for the top layer is 7.86 inches. Then we need to round it to the nearest half an inch, and that's why instead of 7.86, D1 prime or D1 star is 8 inches. After I do a correction of the thickness, now I need to do a correction of the SN1. It's not SN1, it's not 3.3 anymore, it's actually SN1 star, which is A1 times D1 star. So it's 0.42, the layer coefficient of the top layer, times 8 inches equal to 3.36. So this is the end of designing the first layer. The second layer, I'm going to get to the same nomograph. Now I'm designing the second layer. So the only difference between this run and the previous run is what modulus are you going to use. If I'm designing the second layer, I need to pick the modulus of the third layer, the layer underneath the layer of interest. So the same thing, reliability level of 90%. The standard deviation is 0.45. I'm going to hit the turning line, and then from the turning line, I'm going to hit 10.5 million ESLs to the next turning line. From the turning line, now I'm going to pick 12,000 psi instead of the previous number, which was, I believe, 26,000 psi. I'm going to hit the same delta psi, which is 1.2, and now the structural number 2 is 4.7. So remember, this is cumulative design. So 4.7 is actually the SN2 is basically what's from the top two layers, the first and the second layer. That's why here SN2 is actually, again, remember SN2 coming from both. So it's the top layer, which was again 3.3x, 3.36. This is SN1 plus D2 times A2 times M2. So SN2, this is the 4.7, and this is 3.36 plus D2, that's the unknown, times A2, we got it previously, it was 0.12 times M2, which is 0.9. So the only unknown in this equation is this D2 right here. So if you do the calculation following this here, you're going to get a thickness, a required thickness for the second layer equal to 12.4 inches. Again, this 12.4 is not realistic. We need to round it to the nearest half an inch. That's why D2 star is 12 and a half inch. Once you do the correction, you need now to correct SN2. SN2 star now is equal to SN1 star, which was 3.36, plus a 2M2 D2 star. So 0.12 didn't change, zero point 0.9 didn't change, but now 12 and a half inches instead of 12.4. So the corrected structural number 2 is actually 4.71. And with that, we finish the thickness of the second layer. We need 12 and a half inches. Next, we go through the nomograph for the last time, for the third and last time, to design the third layer. To design the third layer, which we call the subbase, I need now to use the modulus of the layer underneath it, which is the soil layer. That's why now we're using the roadbed residual modulus, which is 8,000. So here, the change between this and the previous two runs is only here. I'm going to use now 8,000 instead of 12 or 26,000 as before. The CENG modulus is 90%. The standard deviation is 0.45. This is the turning line. I'm going to hit it with 10.5 million ESAs to the next turning line. And then I'm going to now pick the 8,000 PSI. The same delta PSI is equal to 1.2. The structural number now, the cumulative structural number for the three layers on top of the soil has to be equal to 5.8. And as you could see, by the way, this number has to keep going upwards by the time you go down because it's a cumulative number, cumulative structural number. So the 5.8 is actually accumulation from the three layers. So we got to know that again, so what you can say again, 5.8, this is structural number 3, is actually what's coming from the previous structure number 2. Again, this is structure number 2, which is 4.71. That's why you see it here. So this is 4.71, and structure number 3 is 5.8. If you subtract the 2 and divide them by 0.09, which is A3, and 0.9, which is M3, you'll be able to get the thickness required for the third layer, 13.46 inches. By the way, it's in inches. Then you're gonna round it to the nearest half an inch. Therefore, you need 13.5 inch layer. And now to double check again, you're gonna say SN2, which is 4.7 plus 0.09 times 0.9, which is the layer range coefficient, times 13.5 inches, which is D3 star. Therefore, the SN3 star is 5.805, which is higher than 5.8. Therefore, the design is okay, and you can now draw, excuse me, draw this section. And this is the overall needed section. You need 8 inches worth of asphalt concrete, and you need 12.5 inches of crushed aggregate base, and you need 13.5 inches of sub base. I hope again you understood the concept here, and it's straightforward. You just need to, again, the good thing now, you can rewind the video if you want to, and do a couple examples to understand the concept in more details. One last thing here I want to leave you this with. Sometimes we run into this condition where instead of having 8 inches, because here again the required thickness is 8 inches for the top layer, and instead of the 8 inches, instead of the 8 inches required, how about if we don't have that much asphalt pavement, and we came back and you know what, I only can do 7 inches instead of 8. What should we do? So if that's what it is, then the new design, the new granular base, the layer underneath it, it should be changed to maintain the required structural number. Imagine again, if I'm dropping this by 1 inch, you would expect that the overall structure, the rest of the two layers, has to be increased. At least this one will have to increase, overcome that 1 inch reduction. And that's actually exactly what we did. So if you can go now to the structure number 2, structure number 2 was equal to 4.7. If you go back to the slides, structure number 2 is actually structure number 2 is a combination between A1 times D1 prime plus A2 times M2 times D2 prime or star. So, and instead now of have, we got to know it was 4.7, so that we can't mess up with that. But now instead of, we know that A1 was 0.42, and now if we put a restriction on the thickness of the top layer to be 7 inches instead of 8, the only unknown in this equation now would be the new thickness of D2. So now instead of having 12.5 inches, the D2 will be the new unknown. And if you go through the calculation here, now the new thickness of D2 is actually 16.3 inches instead of 12.5 inches. So you could see that by reducing 1 inch from the hot mix asphalt, we're gonna end up replacing this with 4 inches worth of a base layer. And the question here that some of you may ask, how about reducing it from 7 inches to 6 inches? Or reducing it from 6 inches to 3 inches? Or 1 inch? If there is a minimum thickness of any one of these layers that we can't reduce beyond that, and the answer is yes. The ASHTO book shows us that there is a minimum thickness for the pavement layers, for the asphalt concrete layer and the aggregate base layer, depending on how many easels, millions of easels are we expecting on this roadway. So for example, if I have a highway that we just dealt with, it was about 10.5 million easels per direction, uh, which is in this category right here. If I have a highway that's handling more than 7,000 times 10 times 1,000, which is 7 million, the minimum thickness of the hot mix asphalt has to be 4 inches, and the minimum thickness of the aggregate base has to be 6 inches. So in case you did your analysis and it's the required thickness is 7 and you want to reduce it, you can't reduce it lower than 4. Or in the other situation, if you do your analysis and for some reason you ended up with the required thickness equal to 3.5 inches or 3 inches, you have to pump it up to the minimum thickness of 4 inches for the hot mix asphalt and 6 inches for the aggregate base. But of course, if you have lower amount of easels, let's say I have somewhere of easels between 150 and 500,000, then the minimum thickness would be 2.5 inches for the asphalt layer and 4 inches for the aggregate base. With this, again, we finish this chapter, and I hope again you understood the concept. If you have any question, please you can reach out to me at your earliest. Thank you so much, and we will see you now for the next chapter. Bye bye.